liquids, lecture number 11. So we're going to take this, expand this idea of the intermolecular forces, and specifically talk about what properties those are going to affect in liquids. Next time we'll talk about solids. This time we're going to focus on liquids. So the three properties we're going to look at primarily are vapor pressure, surface tension, and viscosity. And then we're going to spend a little bit of time talking specifically about water and the various intermolecular forces it has and its special sort of circumstance that this leads to in water. So the first one, vapor pressure. So vapor pressure is the pressure exerted by vapor on the liquid. So it's the amount of liquid that sort of becomes a gas above that liquid solution. Right? So that there gets to be a dynamic equilibrium established where molecules can actually leave the liquid, the bulk liquid, and enter the gas. So they're breaking free, breaking those intermolecular interactions to become free molecules in the air. So they're going to exist, and then they can come back. It's a dynamic equilibrium, so they can actually re-enter the solution. Right? So the amount, sort of the vapor pressure, gives us an idea of the amount of gas or solution that's actually able to leave or break out of this bulk solution. And this is going to be a function of sort of the relationship between kinetic energy and the intermolecular interactions. So as the temperature increases, the molecules have a larger kinetic energy, which means that the possibility for them to overcome those intermolecular interactions becomes greater, which means those molecules are able to escape, break out of this bulk sort of medium, and enter into the gas phase. So at higher temperature, we get a higher vapor pressure. Conversely, the stronger those intermolecular interactions are, the tighter those two molecules are held together, the harder it is for them to leave. So a stronger intermolecular interaction is going to lead to a lower vapor pressure. Or, as it says here on the slide, the converse is true. The weaker the forces, the greater this vapor pressure is going to be, because we're looking at how easily it is for that molecule to break its intermolecular interactions and form a free gas molecule. Right? So this vapor pressure is really going to lead to be affected by both temperature and intermolecular interactions. The next property we're going to talk about is surface tension. So these sort of related, right? Surface tension is the attraction that the surface molecules feel towards the rest of the bulk solution, right? As opposed to the inner, something that's on the inside, it's only, you can feel that attraction on all sides. The surface one is only filling it downwards towards this bulk solution. And the surface tension is the amount of energy it takes to pull those molecules apart, to separate those molecules at the surface. So the stronger the forces that molecule is experiencing, the higher the surface tension. So the more force that we're holding that molecule in place, the harder it is going to be for us to separate them to give a indication of surface temperature. Right? This is going to have not a direct relationship with temperature because we're looking primarily at the interactions on the intermolecular level. The next property that we're going to talk about is this capillary action, right? So which is sort of a direct result of this surface tension, right? And what we're looking at there is the ability for water to be, or this liquid to be sucked up into a tube. And that's really going to affect the intermolecular forces are going to affect whether we see a concave or a convex meniscus. Right? So water, we see the concave because the polar water molecules have an attraction to this glass surface, which is also polar. Right? So they want to be with that, and they get some attraction, so they're actually being pulled up the sides, which means the bulk is being pulled down towards the intermolecular interaction. We get this concave meniscus. Something that's nonpolar, like mercury, for example, nonpolar, has only dispersion interactions, it's not going to be attracted to that polar glass molecule, so it's going to prefer to stick to itself more. It's going to sort of move away from that, so we're going to get a convex meniscus. Both of these, again, are a direct result of those intermolecular interactions. What it favors more, the interaction with the glass or the interaction with itself. The last sort of trend we're going to look at in this liquids phase is this viscosity, which is the resistance of a liquid to flow. And that's going to be directly related to the intermolecular interactions as well. The more they want to hang on to each other, the molecules, the less it's going to want to flow away. If we look specifically at water, there is a effect of temperature as well. The increase the temperature, we get an increase in kinetic energy. The ability then to break those intermolecular interactions and actually flow away increases. So they're a relationship to the stronger the intermolecular force, the higher the viscosity is going to be, the greater it's going to resist flowing. Also, as temperature increases, you typically see a decrease in viscosity because the kinetic energy is allowing these molecules to separate more fully. And so all of these sort of properties of these liquids are based on this intermolecular interaction and how easy it is for the molecules to overcome their intermolecular interactions. Either generally, we talk about a single temperature, or as we increase the kinetic energy. So let's take a minute and then talk about water. Water has, we've sort of alluded to it in some of the other lectures, the special properties of water because of the presence of this hydrogen bonding. Because it is polar and has this hydrogen bonding, it makes a very good solvent. It's able to dissolve a lot of polar molecules and a lot of other things by able to break these ionic bonds, if you will. It also has a fairly high heat capacity because it takes a lot to actually break apart those intermolecular interactions. So it requires a large amount of additional heat to break those molecules apart, giving up a higher heat capacity as well as a fairly high boiling point. The surface tension and viscosity, or the capillary action for water, again, has a fairly high surface tension because those strong intermolecular interactions. If we look at the three-dimensional surfaces when it forms ice, we'll talk more about solids in the next lecture, but if we form ice, we actually get a hexagonal sort of opening. That when it forms that solid, because of this intermolecular interaction, this hydrogen bonding, the molecules actually form a fairly regular pattern, which is going to cause the density of that solid to be lower than the liquid, which means that ice is going to float. So this hydrogen bonding in water, along with the bent structure, is really allowing water to play a pivotal role and have a lot of special properties, as you can see in this chapter.
Dad, I done did it.